on this computer. So, so I have to just kind of give you a heads up about an unintentional trolling that's occurring in one of your exercises in the textbook. Okay. First off, I've posted this. There's no active time limit. In other words, it won't submit when you get the 45 minutes are up. You can submit it after 45 minutes. Okay. Just letting you know that 45 minutes is the expected time, and then I'll probably try to figure out how to go back and account for the late penalty. Okay. But the quiz has been posted. It is due February 15th. You need to make these all due at like 11 p.m. instead of this midnight time, but regardless, for these ones, it doesn't matter. All right, so what is this ridiculous amount of trolling I'm talking about? So if you go into your chapter 6 exercises, have any of you tried this one down here? Create a string representing the quote from the first Black woman in space, Mae Jemison. Any of you do that one? Try that one yet? I know I saw somebody on Discord try it. And you probably ran it. If you did try it, you're gonna go like this. Okay, so I need a string to represent the quote. And then you're gonna try using the split function, which is one of the things that's covered in the textbook, to figure out how to break it into 4 pieces of text based on the occurrence of the period. So in other words, print it out sentence by sentence by using the split function. Okay, and you might try it and you'll say, hey, it didn't work. Right, so if I like do quote is equal to, and I just copy pasted that. Oh, weird. That by the way is an expected weird on my part. Well, now it's a string, right? And we try, and you'll go, hey, okay, I'm going to run this code and try to get it on the check to check against this stuff. And anyway, what you'll do when you run this. Sorry, what happens when you run this? Okay. I should say is that you'll get something along the lines saying, hey, when you print it out split, it will say, it'll look like it should match, right? But then it will say like the second sentence doesn't match what's expected, which is that's just not true. And you're like, but that's just not true. That looks exactly like what I should be printing out. So here you're being trolled because what we copy pasted here, right? Something happened, right? What happened when I copy pasted there? Did it copy paste double quote marks? No, copy pasted what you'd see in Word, which are the non-symmetrical quote marks, by which I mean, or sorry, the symmetrical quote marks. So this one, an open quote and a close quote. But in Python, use that. In other words, these are non-Unicode, non-ASCII characters. It's one of those weird things that when you're working with text that sometimes occurs. And this is like the only time I think it occurs this semester, but it's worth noting. So similarly, when we get a failure state for the second sentence, we have, let me grab that second sentence, and I'm zoomed in. I'm going to zoom in a ridiculous amount so that you can see the text. So that's, whoever coded the test wasn't looking for that apostrophe S. When they wrote the test, they were looking for, and that looks different, doesn't it? When you zoom in like crazy. So just note that sometimes when you copy something from like Word or stuff that's formatted HTML with quotation marks, sometimes it's just a little bit off if you're trying to go for like identical. Most of the time it doesn't matter. Yes. Well, that's because you surrounded your string in single quotes, most likely. So if you want, so either surround your string in double quotes, or when you get to over here, do a slash to escape it, like we did in the very first lab. So just FYI, like, this is what I keep getting at to this. Like, sometimes what you're seeing is not actually what you think you're seeing. Sometimes, and this doesn't really happen too much with, this doesn't really happen these days that much unless somebody is actively trolling you or they write a bad test. In which case it was this case of bad test. But like if you typed it out character by character, it would work for you. So anyway, if you completely forget this and you have no idea, just remember that you had something with this problem. You can post it on, ask on Discord for help, right? Discord is a great resource. The people get answers very quickly to these questions. Like I look to go and answer, I see a question, I get to around it being, I get ready to, and eventually I come around to answering it, but it's already been answered. So that happens a lot on Discord. All right, so that is what I've got. I just, that kind of heads up there. Now, let's talk about one of my favorite comics of all time, XKCD, which if you don't know what it is, ooh, okay, that he did do. So like it's a Monday, Wednesday, Friday web comic. This is today's comic control group. Are you playing Wordle? No, I'm in the control group. My new all-purpose excuse for when I'm not doing something. So anyway, he writes a lot of kind of tech-based comics on math and similar with math and computer science. So copyright, that's an early one. Let's see. This one about did you really name your son Robert? Close quote, close break, parenthesis, semicolon, drop table students. Yes, little Bobby Tables we call him, which is talking about, this is talking about, you know, a SQL escape, essentially where if you don't safeguard your inputs when you're working with a database, a SQL-based database, if somebody puts in the wrong text, they could enter in arbitrary code and then actually make you run code like delete database tables, which is hilarious in my opinion, when it doesn't happen to you, and horrifying when it does. So anyway, going back to this, today's exercise, you go to Runestone or you can click on it. It was what we were going to do on Tuesday, but I thought it more important to do Thursday's lecture for reviewing on Tuesday. So over here, if you scroll all the way down, and I'll link, or I scroll to the Canvas page for Module 4, you can find it linked. And I will also drop it for everybody in Zoom. I can drop it for you here, which is generating a XKCD, a password XKCD style. It's based off this XKCD comic, by the way. So here, oops, and I will give everybody just a kind of a minute to get to it. Again, you can find it on Canvas, or you can go to your Runestone, the Runestone page, scroll all the way down and find it there. And so today's exercise is going to be working on generating an XKCD style password, which is to say that like passwords suck. And you probably have to change your password a lot. Although actually Temple's really good about their password policy. I really like it because it's like somebody read this comic. So typically like you're given requirements for writing passwords that are silly, like, okay, it has to have so many, you have to have, it's got to have one letter, uppercase and lowercase letters. It's got to have a number and a symbol. It's got to be so long. So typically somebody might do troubadour like this, which is a not really common word. Random capitalizations, random but common substitutions, like for an A. And then, okay, I'm going to put in a punctuation mark or a number at the end, right? Like, and you can add a few more things, but the idea here is that there's only it creates this kind of a amount of space, this entropy, this idea of basically there's only this is a possible search space I have to look through to try to crack your password. Okay. If I'm trying to crack your password. And the idea is, maybe if I take 1,000 guesses a second, it should take about 3 days to crack that password. If you give, with something like that, not that hard for a computer to do if it's targeting you specifically, but for a person to remember, it's annoying, right? How many times have you done that and oh, what did I put where? What are the symbols there? I mean, you can use something like a common based password and manipulate and alter it based on the other one, but honestly, it's hard to remember. Or you could use a something that keeps track of all your passwords and generates random passwords, which is, to be honest, what I do. But what if I lose that? Well, I'm out of luck, basically. I primarily use that for websites that aren't really dependent. For things that I really care about, I need to have stuff like that. Now, on the other hand, you could do it this way instead. 4 random common words, correct horse battery staple. That produces way more, because it's a longer password, it creates way more space that you need to search. Way more space for computer to search. About 44 bits of entropy, he puts it in, and then it says, so even though it's hard for us to understand the power of exponents because we just don't think of numbers this way, 2 to the 28th versus 2 to the 44, that's a couple days versus half a millennium. Okay, and how easy is it for you to remember? That's a battery staple, correct? Right. So the idea here is that longer passwords made up of common words are easier for humans to remember. And if you actually check Temple's, the Temple IT department, the password policy they set up, the longer you make the password, the short, the less complexity it needs, because long passwords are hard to break. So something where you've got 4 words or some kind of sentence like that, that's actually a really good password. Okay, and it's in the subtitle. This is 20 years of effort. We've successfully trained everyone to use passwords that are hard for humans to remember, but easy for computers to guess. Because it used to be okay, let's think about, it's got to be at least 8 long, and then those other requirements are for people to prevent people from doing password as their password, because people are lazy. Look at this. Most common passwords. Most common passwords. 1 2 3 4 5 6. Password 1 2 3 4 5. QWERTY. Although that's for US passwords. If you're working in a separate country that has a different keyboard layout, because they do have separate keyboard layouts in different countries, you might see a ZERTY or something like that. So yeah. Anyway. Yeah, quartz. All right. So let's figure out. So let's go ahead and start by. So this exercise is going to start by creating a traditional random password composed of letters, numbers, and a few special characters. So here they've helpfully given us some code. Namely, they've given us letters, capital letters, and numbers. And it says, make an 8-letter password by combining the characters from the 3 strings. Okay. So there's a couple things here. This is a random kind of generation. So we're going to need the random library. Now, the random library, if you haven't gone around to watching the videos or reading the textbook on that, is pretty awesome. It does randomness, except that's a total lie, because we need to get into because that is a philosophical discussion. What does it mean for something to be truly random? After all, if I had a rubber ball and I threw it and it bounced around, you could argue that the way it turns out is random. Or if I had a die, right? I roll the die. That's a random outcome, except that the inputs that I put on the die, they could be tracked, graphed, predicted, right? Computed, and it could calculate what side it's going to land on. If you knew everything about every little thing about the forces I were putting on that die, and the pressure in the room, the way the air was moving, that could technically be used to compute it. Is that truly random? Is anything truly random? After all, I'm just a squishy brain with shooting electrical signals. Can't that be predicted at all? And the answer that statistics have saying, well, that's not very useful for our purposes over here. We need when we say random, we need something that is statistically random, right? That it follows some kind of distribution, typically uniform distribution. What does it mean for a uniform? Your most common distributions. Your most common distributions are uniform, where basically all the possibilities have the same output, or a bell curve distribution, meaning that most of the outcomes are in the middle. A uniform distribution you typically see with one dice roll. A bell curve, that's more like if you're rolling 2 dice at the same time. Get it with stuff like height, weight. So anyway, random is pretty cool because it allows us to kind of just do statistically random stuff. Okay, so the first step we're going to do so there's a couple things. There's a couple tools here, okay? So the first is that there's a function built into random over here called random.choice. So random.choice letters. And that takes in a sequence, which can be either, as we've learned, a string or a list. In this case, it's a string. And it will choose one of those things from that sequence. So I'll just go ahead and print it and run it, and it will be fairly obvious as to what's going on here. K, X, W, E, T. So that sounds like a public radio station of some kind, So, so it's choosing randomly a letter from this. And it will probably uses a process based off what's called the Mersenne twister, which sounds like a kind of dance, but you can look into detail about how random numbers are chosen. It's its own kind of subfield, and way too much to go into in this context, but it is interesting. So each time you run it, you will get statistically random. It doesn't mean, like I saw a T again. That doesn't mean that this isn't working, right? These are independent random choices. So any number is just as likely, any letter is just as likely to come up. Okay, so we can use random.choice to get some kind of, we can, to select some kind of outcome. So I could even store it in a variable. Outcome is equal to random.choice letter, and then print the outcome. All right. So that's one kind of key there. That's our first kind of key. Our second key is that honestly, all this stuff is asking us to make an 8-letter password by combining characters from all 3 strings. Now there's a couple ways you could do this. The first way is that you could have a couple different, you could have like a nested random statement, like randomly select one of these things, and from one of those things, randomly select one of these. Honestly, that's just kind of, that's a bit much. Instead, what we could do is that you can combine these things by concatenating them. And I'll call it alpha num is equal to letters plus caps plus numbers, right? That makes sense to everybody? And now if I run random.choice letters on AlphaNum, my outcome won't just be lowercase letters. This created a new string that's the combination of all these 3 sequences added together. So run JZAV, capital R, 0, R, I, M. So it weights each of these equally. So that's, I find, the most straightforward way to do this. Yeah, random dot choice is a uniform distribution. There's other functions you can do for non-uniform, but most of the time when we do stuff like this, we almost certainly want a uniform distribution, because how would we know how to like just distribute like where the normal distribution should go for things like this? So we keep getting more, so we can keep generating random numbers and letters all day from this. All right, so the third key for this is the accumulator pattern, right? We want to generate an 8-letter password, which means we should generate 8 letters and accumulate them. And you can accumulate things just like you can accumulate strings just like you can an integer, right? What do I mean like that? Well, like I could do this. For, let's see, output is equal to 4 in letters. No, sorry. Char in letters. Output plus, so is equal to output plus char. Oh, that's going really well. Come on. Print output. And as you can see, what I've done is that output gets each of the takes each of the letters from here in turn and adds them to the output. Now this is the empty string, meaning it's a 0 length string. It's a string with nothing in it. It's like less than a blank space. It's like the kind of the space between spaces, right? So it's 0 length. But anyway, so adding anything to, anyway, since it's like it's like the number 0. And like the number 0, if you add anything to it, your result is whatever you added to it. So you can accumulate stuff like this. So I'll go ahead and share the code I have with you. You can reload or work it with what you have over here anyway. And what I want you to do is use these 3 parts. Take about 5 minutes to try to use these 3 parts to generate a fully random password, right? To generate an 8-letter password by combining the characters from these 3 strings. In other words, select 8 things from alphanumeric and put them into one big string and print out, or one 8-character string and print it out for me. Okay, so I'll give you 5 minutes to do that. When you're done with it, and when those 5 minutes are up, I will do that problem as well and show you the answer. And don't feel bad if you can't get it done in time. It may just be that you didn't understand what I was talking about. So let's go ahead and I will pause the recording because otherwise nothing interesting is going to happen. All right, so whoopsie, there we go. The mouse got a bit overeager there. So what we're going to do is that we're going to make ourselves up. We're going to go ahead and first thing we need to do is take all this stuff and put it over here. We'll combine all those alphanumerics into one thing. We'll set up our output like this. Now for every character, now we want to do this loop 8 times specifically. That's probably the biggest change over there. We want to do this loop 8 times. So to get 8 characters, we need to change this loop. For blank in range. And yeah, I may have just primed you to try to use the iteration loop. And I realize that now. I'm sorry for that. But what we want to do is for blank in range 8, because we want to repeat whatever we're doing. We want to repeat selecting 8 letters, selecting a random character 8 times. And what we do is we say output is equal to output plus random. Well, we can just do this. Outcome is equal to random not choice, select that alphanumeric character. Say output is equal to output plus outcome. Although that's a bit wordy, I might just call it car over here and car over there just to make it a bit, more readable. And then I can print out the output. Whoopsie, except I totally just, I meant to hit F5 because, that was embarrassing. I meant to hit F5 because that's how you typically run things. But no, I just refreshed the page and lost the work I did, which is not that bad because random. Again over here. Yeah, I'm just going to go ahead and I'll just be a bit more brusque about it in this version of the solution. And save and run. Error, modules not callable. Random. Oh, yeah. Output is equal to output. Oh, I typed random there and I meant range. No, no, that's what happens when I talk and type at the same time. So there I'm getting a randomly generated, here I'm getting a randomly generated password, which is honestly, this looks like a nightmare to remember. Okay, so now let's follow the same, now that I've done that, we'll follow the same kind of process to do this, where we make an XKCD model, an XKCD password by selecting 4 random words and concatenating them together. So we'll select 4 random words. Now notice here we have lists of words, list of strings over here, and it works exactly the same way, right? Just remember you got to import random at the top to use your random, and we can just do print random dot, and just as an example here, because you're going to want to combine them just like you did over in the other thing. Random dot choice nouns, right? And run it, and it works exactly the same, except we're going to be getting a random word rather than a random letter. Why are we getting a random word? Because it's a list of words. It's a list of strings. So we aren't selecting a single random character, because that's not how because that's not what lists are made of. Lists are made of things. If I had a bunch of numbers in here, like 8, 5, right, you get the idea, and I'm just going to stack this up with way too many letters to try to outnumber stuff. You'll see that I also select some letters here every so often, that I get a number in here every so often. We should totally not do that because that looks awful. Instead, do this. So import random, and you can do the same random selection. So the pattern should look exactly the same as above. So go ahead and take 3 minutes to do that one. Okay. So, take 3 minutes to do that one. And yes, I will share this code, the above code. Okay, so I've shared the above code, and cue the Jeopardy theme again. Was recording, right? So let's go ahead and make this let's go ahead and make a new variable, words or whatever. It's going to be the now. So you can, one of the cool things I love about Python, that's again not a feature in other programming languages, so you can totally concatenate, is again strings and it's not in programming languages like Java or C. You can treat strings and lists pretty much the same, do the same operation, the same very powerful operations on them. Nouns, verbs, and adjectives, right? You can do that and you can get a completely new, no need for this print words, but you can, I'm just kind of demonstrating. You can add them, you can concatenate them all into a new thing, which is awesome, personally, I think. So let's keep going. So now it's just follows the same thing. We need 4 word password. So 4 in range 4, which is mildly funny because we've got a homonym, whatever you pronounce it. Okay, and now we say Now we need something to accumulate with. Let's call it password is equal to empty string. Password is equal to what we previously had as our password plus, and then random dot choice, our random choice of our words, assuming I can spell woods. Okay, and no, we don't hit, like I've got a reflexive, reflexive motion to hit the F5 button to run the program. You're gonna get me into trouble. So I have no output. Darn, what did I do wrong?
Forgot to put print.
I forgot to put print. It's a very common mistake. I still made it. That was a not deliberate mistake on my part, by the way. Not total. I immediately know what the issue is when that happens. It's just a matter of, oh, right, that was embarrassing. Right, great. And so, right, again, computer's an evil genie. He's going to do exactly what you tell him to do. Or she or it. You can gender your computer however you want it to. You know, it's a rock we tricked into thinking by shooting it with lightning. So we can anthropomorphize it however we want. Wish evil shorts dip. Encouraging consent born improvised. Quality appreciation isolated tune. Extreme mind delay shared. Closer clean developmental gray. I don't know why that one tickled me so much. So sounds like some corporation is trying to figure out the exact palette they're going to build a building with. Okay. So of course, occasionally your IT department does, honestly, our IT department is pretty good, but the IT department at your work or wherever may not be so happy with that password. So we're gonna have to. They want us to have at least one capital letter and a number in our password. So we can replace so there's a couple ways to do that. We could do a replacement, like say replace. So for instance, you could use the replace method. Pool.replace O with E replaces all the O's with E, so that gives us peel. So we could do like A's with 4s. We could replace all the A's with 4s, which again gets us to the end of it. Honestly, personally, I don't like that. If we're gonna do something like that, something silly like that, we should just add a letter to the. I would just capitalize the first letter and add a number to the end and be done with it. All right. And because but we've got this cool, but what's cool over here is that we've got a couple of functions that are useful, right? I think I showed you upper when I was writing a function a while ago, on Tuesday, that was a while ago, and upper makes the word shouty. It capitalizes it and puts it in capital letters. Peel and peel. Lower will do exactly what you think it does, and capitalize is pretty cool. So because it's a useful thing that you don't really think about needing until you have it, which is like if we want to make it horror movie-esque, like the pool. Let's go ahead and print out the word, and then see capitalize. Let's see, how does capitalize work? Docs, Python, capitalize. Capitalize. The keyboard on this thing is not great, but again, I use this laptop for a very specific reason, which is for these kind of lectures. Okay. So capitalize. String.capitalize. Returns where the first character of the string is capitalized and the rest is lowercase. Change, the first character is now put in title case. This means that characters like digraphs will only have their first letter characterized rather than the full letter. What in the world are they talking about there? They're talking about weird words like this. Lowercase digraph, AE. And so what it's saying is the change they've made is if you have this digraph, it will work on it now. Capitalize the characters. This means characters like digraphs will only have the first letter character capitalized rather than that one. Let's see what else they have. They have any other ones? So yeah, there used to be some weird kind of things like that. Characters that aren't really, there's a lot of characters that have fallen out of use over just, you know, centuries of use, like the Thorn character. Which is that this is TH, the TH sound. Don't know why it's called the Thorn character, but anyway, that's there's just characters that that have just fallen out of usage, like those weird long, you know, what are they? S's in like the Declaration of Independence. So I guess whenever somebody complains about not teaching cursive, you can complain about the loss of the Thorn character too, you know. Anyway, so capitalizes the first letter of the text. So pretty useful for making your password. So let's go, I'll go ahead and do this one now. So we've got our word generator over here. I'm going to go ahead and copy and paste it over here, right? And now let's go ahead and capitalize this. Password is equal to password dot capitalize, right? Now, notice that I wrote password is equal to password dot capitalize because it's very important that I do that. But if I didn't have that, I get this. Whereas if I do have it, thank you, history, I get this, where the first letter is capitalized. Now, this is because strings are immutable. You cannot change a string. You can never change a string. Once made, always is. Until we empty out our memory and all is lost to void. In other words, it's all, once you make a word, it's there until our program's done with it. So you can't actually change any strings you write. Instead, anything you do like capitalize or uppercase, I've said it capitalizes the string or makes it uppercase. But in reality, what I'm doing is I'm making a new string that is a copy of the old string, except it has this change applied to it. So here, when I do password.capitalize, I'm creating a new, I used to have decrease wasted 8 repeat. Sounds like a demotivational or something like that. But anyway, we used to have that lowercase, it originally had that lowercase one. And then when I ran password.capitalize, it stored this string, it created this string and stored it in password. And then in fact, we kind of discarded the old one, but we did not change it. We got rid of it, but we did not change it. Make sense? So we made no change to to that. And now let's go ahead and just add on our random letter as well. Sorry, our totally random number added to the end, because honestly, we should not have to. Honestly, our password's strong enough. So that's good. All right. So now so I'll go ahead and share this one. And if random is not defined, you did not import random. So you got to remember to import random, and we always like to put our random statement at the top. So it's very easy to miss if I've been kind of down here working like this. So random it's not all programs need random number generators. A lot of them don't. So this last part we're gonna take a look at, and I'm gonna help walk you through, is kind of the reverse of what we've been doing so far. Which is to say that and it says we're gonna be, we have a bunch of extra code here that I'm gonna walk us through, okay? Because right? And all we're gonna change is all the stuff between line 11, between line 10 and 12. We're gonna add more lines there. So there's a lot more going on there, but let's talk about what the challenge is. The challenge is that we're gonna go in reverse. Given a password, in this case, the person's password is ABCD. Given a password you don't know, we want to see how long it would take for the computer to crack that password. Okay. And we're going to be as dumb about this as possible. I'm just going to try random passwords until I find the correct one. Okay. So yeah, this last part goes beyond what we'll have covered in this book so far, but I'll give you extra code. Probably be able to figure out what it does, and it'll be a fun preview. Let's suppose you do have a 4-character password composed of only lowercase letters. That's useful, only lowercase letters. How many guesses would it take you to guess the password? You can actually write a program to create a 4-letter string and compare it to the known password. If we put this process inside a loop, we can keep the track and see how many guesses it takes to find the matching password. So first off, if I'm trying to guess let's just talk about numbers for a second. Okay. Which is, I need to share whiteboard. Okay. That wasn't helpful because it came on the other monitor. So stop share whiteboard again. All right. Hopefully everybody can see. Can everybody see? Especially online? Got just a white screen right now. If we've got a 4-letter password made up of, again, lowercase letters, there's 4 of them. How many possible passwords are there? Which is, well, we answer that by basically saying, hey, how many choices do we have for a first letter? We have 26 possible choices for the first letter, right? We also have 26 possible for the second letter because there's nothing that prevents us from using a letter again once we've seen it, right? Like, for instance, could be a password. Not a very good one, but could be a password. So we have 26 times 26 times 26 times 26. So in other words, 26 to the 4th, which is actually a big number because, I mean, honestly, let's just toss out, again, let's simplify this. What would 20 to the 4th be? That would be 20 times 20 times 20 times 20. Right, so 20 times 20 times 20 times 20. And again, when you're doing this kind of math, it might just be easier to break stuff up and cheat, because that's equal to 2 times 10 times 2 times 10, right? Everybody agree that each 20 is equal to 2 times 10, right? And so we could say, hey, that's equal to 2 to the 4th times 10 to the 4th, right? And suddenly the math becomes a bit easier. That's a 10 with 1, 2, 3, so 4 zeros. And then, or 1 with 4 zeros behind it, and a 2 to the 4th, that's 16. That's just one I know off the top of my head. So that's a pretty big number. That's a big number, but not insurmountable. Okay. Whereas if I had 8, it's utterly ludicrous. So let's go back to our code for a second. Or at least ludicrous for my puny human brain. So let's take a look at this code now. It says import random and import sys, short for system. Okay, which does some stuff that are based in the app for that, well, like are useful for like system commands and things for running with Python. And for instance, the third line is set execution list 60,000, which gives us the parameter 60 seconds. Now, the way that this
specific interpreters set up. Sorry about that. The way this is set, that your runestone is set up, is that it's set up to assume that you're going to make a mistake at some point, and that if your program's running too long, then something like an infinite loop happened. Right? If you write an infinite loop, which you can do in Python, it will just run happily until you decide to exit the program. Okay, which you can easily do by clicking on the window or hitting this Control C or Command C to terminate the console. Right, not a big deal there, but on web page, it's not. That's a bit more involved. So it says like if it runs more than 30 seconds, it's just going to turn it off. So this line over here increases the execution limit, the time limit that it gives before it crashes the program, to 60 seconds. Right? Yeah, specifically, it says your execution time limit is 60,000 milliseconds. Right? That's what the 60,000 is. It's measuring it in milliseconds. So here, my password is ABCD, guess number. So here, this is what we're going to use to count the number of guesses we have. Okay. So done is equal to false, and while not done. So this is a while loop. So we have two types of loops in all programming languages. We have, and if you want to be a real pedant about it, it's there's three, the for each, and the while, but honestly, it's just the for and the while. Okay, but we've got the while not done. While is a different type of loop we'll be covering later. They are what are called indeterminate loops, or that is what they're primarily used for. For loops are determinate. They have a determinate amount of time they run for. For instance, this loop ran 4 times. Whereas other loops I wrote, like one that went over all the letters, it went over it 26 times, once for each letter in there. With a for loop, those are good for saying this, it will run this specific number of times and no more, no less. While loops are useful for when you don't know how long it's going to take. For instance, user input, like when you ask the user to enter a name and they mess it, or sorry, when they ask the user to enter a number and they mess it up somehow by like typing Apple in it, or the word 3 instead of the letter 3. There's no, and remember, humans, and I include myself in this statement, are dumb, right? So I include myself in this statement. We find all sorts of ways to mess things up. It's one of the challenges, actually. One of the fun anecdotes I find of like of working with the forestry service, not that I have, but like people who have, when they try to design trash containers that are easy and that are easy enough for the dumbest of humans to open, but not for the smartest of bears to open. And there's unfortunately a significant overlap between dumb humans and smart bears. It's one of those kind of design challenges there, because a determined hungry bear who smells food, he's going to try hard. He's a mammal. Good for him. He's got a brain. So anyway, while not done, this means that basically while this condition is while this is true, not done. Done is false. False means not, we'll flip it around. So in other words, while we're not done, this will run until done is true, in other words. And as you can see over here, we'll be flipping done to true. Okay, so again, this is a bit advanced. This is what we're getting into in much later weeks. I'll be covering the if statements next week when we learn to blame one of the former popes for all of our problems about leap years. I say that facetiously. It's the Gregorian calendar is an awesome invention. It just really, people don't really know how leap years work. We really don't. You really don't. You think you do, but you don't. You really don't. Okay. Anyway, so while it's not done, if guessed password is equal to my password. So in other words, if we found the correct password, we're going to print out the number of guesses. Then we've got this conditional statement over here saying we found it after this many guesses, and then flip it to true. So what we're going to do is that, for simplicity's sake, I'm going to go ahead and do some copy pasting. right? Here's all the letters and here's a random. Great, copy. Oh, it already had a random. Awesome. Paste. No need to have an import random. That's just stylistically bad if you've already got one, right? Why would you tell, but your computer's a good listener. Why would you tell it to do something twice, right? So there's our letters. Honestly, it's probably best to just put this outside of the loop because, right, here's the letters. And what we're going to do is that our code is going to go over here and we're going to say, okay, what should I do? I want to create a new random password, right? Made out of the four, it needs to be 4 letters long, right? So password, so we've got this variable guest PW. Okay. So what we're going to do is we're going to say 4 in range 4 because we need 4 random letters, right? And we're going to say guest underscore PW plus this area is equal to guest underscore PW. And honestly, the reason I don't go the reason I was going a bit slow there is to check my spelling, because that's one of the most common mistakes you can have where you accidentally misspell something. So guest password is equal to guest passwords plus random dot choice letters, which I just pointed to my screen as though you can see what I'm pointing to on my screen. Letters, which we just copied and put over here. Okay, so we're going to guess that. And if that guest password is equal to the password that he has set over here, then we'll say, hey, we found it after this many guesses. Okay. And so done is equal to true. And statistically, we're not going to see the same password. We're not going to like guess A, and then we're not going to guess A again. It'd be very unlikely for me to keep guessing the same letters over and over again. So random isn't using randomness to try to brute force this password, because that's what this is. This is a this is what we say when it's brute force. Using random kind of stuff to guess this password isn't a bad strategy. So I'll save and run it, and you'll see that it's kind of locked up my screen. It was kind of laggy a bit, not responsive, because it's honestly eating a bit of processing power at the moment, trying to guess this password, and found it after 0 tries. That can't be right. Why is it only 0 tries? Yes. That's exactly right. I have to, guess it's doing exactly what I told it. Now that one was a deliberate mistake. At least that's my story and I'm sticking to it. But anyway, but seriously, it's a deliberate mistake here. And I was trying, and the thing here is that we do need to have, not only do we need to accumulate this, we have to accumulate the guess number as well. We want to keep track of how many guesses we did. We don't do it inside the loop because then we would increase it by 4 each time, right? If it was in the loop, we'd increase it by 4. So once we're done creating a guest password, we're going to increment guess number plus equal 1, which again is the shortcut for guess num plus 1 is equal to guess num plus 1. So now, oh, that one quickly found it after 78,435 tries. So it's actually doing quite a bit in a very short amount of time, which is fascinating, right? Now again, let's go, so 58,000 that time. So let's go ahead and open up our calculator here and actually figure out the correct answer to our previous question, which was 68. So 26 to the, oh, right, this resizes 26 to the 4th power gives which is how many possible 4-letter passwords they are, gives us 456,000 possible passwords. And it took us 456. So it took us 588,507 tries to guess that password, which means that my guessing is kind of inefficient. The way I was doing this was kind of inefficient because guess what? If it took me more guesses than there are combinations, then I kept hitting the wrong combination again and again. Sometimes it's going to be lower, sometimes it's going to be higher. You know,
Oh, this one's taking a while, so we'll see here how long this one takes. Yep, took 475,000, so slightly unlucky that time, where I repeated a bunch of passwords, but that's okay. Yes. So if here we know how many if it is, we would use a couple of different for loops if we didn't know, where I would try on the 4-letter passwords and the 5-letter passwords and the 6-letter passwords. Yes.
Is there any way to program it so it doesn't type in the same answer?
Ooh. Yes, so there's 2 ways for that. We could keep track of the passwords we generate, which is wasteful, or we can go a bit more methodical about that and say, hey, but that requires us making, and the only reason I didn't do it this way is because it's kind of a, you'll see, I'll do it right now. It looks horrifying. So for letters, and now I'm going to need a lot of copy pasting for letter 1 in letters. Okay. No, pay attention to what my keystrokes are, please. Not you, the computer. And as you might guess, 2, 3, 4. Guessed password is equal to except now it's 3, 2, 1. So that's how you do it without any repeats. What I did there is I said, okay, for each letter in letters, let's try as letter 1, let's try each of the letters. And we're going to do that for each of them. So let's start with A, then A, B, then C, D, E, and so on and so forth. And then when we're done with all the first 26 of letter 4, letter 3 is going to go on to its next one, which is going to be AABA, AABB, AABC, AA, and so on and so forth. But we're not going to get repeats now. At least we shouldn't. All right, except for one issue. Stop this page. Yeah, didn't fully finish it out because it's going to go through all possible combinations each time. So we're going to let it void out. I did not. That's how you get all the combinations, but I just simply went through all the combinations, which it's doing the evil genie thing, because I'm going through all combinations, and then it incremented that guess by 1. And then it says, hey, is that very last combination you went through the thing you were looking for? And my answer is no. Okay, now let's go through all the combinations again. So it should crash after a minute. And apparently when you make an embarrassing mistake, a minute's a long time. See, okay, see, it exceeded the time run limit. Let's go ahead and limit that to 15 seconds right now, because honestly, I've made it much more. So now, but because of the way we've done this, right, we can figure out what we can say, hey, this is the guest password. So now we can actually indent all of this into this now, because we're going to be going through each of these sequentially. And now, also now the while this while loop is not necessary anymore with the way I've got it set up. It found it after 732 tries. It's always going to find it after 732 tries because it's going through all the possible combinations in the exact same order. Also, again, as I should mention, the way I've run this now, because I'm going through every possible password, that while loop is no longer necessary. So I'll just select it all. I select, and cool thing you can do,
you may not have fully appreciated the fact that, you know, if you look at your tab button, it has the arrow going in different ways. If you hit shift tab, it de-indents it or dedents it the other way, which is pretty cool. Okay. So, okay, we've got that code, which I'm going to go ahead and share. All right. And now, so we can see that if we're guessing randomly, it varies pretty wildly. But what happens if we do it to 5 characters? Or what would happen to the possibilities so what happens to the possibilities if we have 5 characters, right? It's just 26 to the 5th power, right? So that means that by increasing it by 1 character, we increase the number of possible passwords by a factor of 26. What if we allow it to include all uppercase characters? Well, that changes the base of those exponents from 26 to 52. And so those change that number. So let's go ahead and do some calc. And so here, it just wants you to try some calculations. When you calculate the number of possible 4-letter passwords using just 26 letters and 4. Yeah, and we've done that. And honestly, it's just print, right? 26 to the 4th to calculate that many. Now, what if you allow 26 letters plus 10 digits, right? 26 letters plus 10 digits. So those 10 digits now add 10 more characters. And that is that's 4-character password. And now, what if it's an 8-character password? And we'll see when we change it up to an 8. These passwords, that goes up to a huge number, which is 1, 2, 3. So this is millions, billions. So it's up to 2 trillion now with 8 characters. Okay. And if we up it to 52, so if we upped it to 62, right? So if we do uppercase letters, lowercase letters, numbers, and then no symbols, okay? No symbols yet, because there's an arbitrary number of those, right? That brings us up to 1,000 mils, bills, 200 trillion, okay? But that's nothing compared to what happens if we use a bunch of letters, if we use a long password with just short things. So like, for instance, let's take a look at something that is correct or battery staple, or at least something that is 16 letters long. So 4 4-letter words, okay? 4 4-letter words to the 16th. Power exponents are extremely powerful. And we'll see that we've got a ridiculous, that number became, it became longer in a way our puny human minds just can't appreciate, right? This is thousands, millions, billions, trillions, quadrillions. Now what's over 4? So we've got 5. Heptillion? Hexillion over here. So we're in the hexillion range. I mean, it's hexillion, synonym of sextillion, the 6th power of a million. Although actually, yeah, names of large numbers though, just for our last thing. The way I'm counting may be foreign to you if you are coming from a Commonwealth nation. That is one of the ones that's been part of the UK Commonwealth. Okay. Because notice over here, we've got million, milliard, billion, billiard. Short scale, long scale. So if you're coming from French Canada, you might end up using the long scale, where numbers are given different names, which is slightly confusing. So short scale, million, billion, trillion, quadrillion. But a million, whereas a billion in the long scale, a billion is a million million.
as opposed to 1,000 million. So now this probably won't come up too much. And this is part of the reason why everybody uses scientific notation in science documentations and mega giga tera peta. But again, it's just one of those things to be aware of, that if you happen to be working with anyone there. So, yeah. All right, but anyway, let me go ahead and share those two documents with you so that you can run them and get credit for them. Share. Yeah. Okay, boom, boom. So, but yeah, these big numbers are hard for us to comprehend. They really are. So be sure to fill out this survey down here about how well this went. And then next week we'll be doing a number of in-class exercises that I don't think are on Runestone. I think I know at least one of them isn't, which is the leap year one. The leap year one we'll be doing in class is a former assignment I used to give, and I've just turned it into an in-class exercise because I found it was. What I love about that one is that it will be a difficult one. I'm sorry, it will be non-trivial for everybody, including people who have tons of experience programming. It's non-trivial, and there's not a loop to be seen. It's all if statements. All right, so you're all free to go. See you next week.
Thank you, Professor.